Welcome. This is Dean Waldo from the Department of Chemistry, Pacific Lutheran University, and this is a short online lecture supplementing the class lecture for physical chemistry. And this is discussing further information 3.1 from our Atkins textbook, and we're going to think about extending the idea of molar Gibbs free energy and how it changes with pressure into treating that for a real gas instead of an ideal gas. So which is going to give us the idea of fugacity, and that's right here. That is a Latin word, or derived from a Latin word meaning fleetness. A little point of trivia, I guess. So what we've seen already is that the molar Gibbs free energy at some pressure P can be calculated from knowing what the Gibbs molar free energy is under standard conditions, and this term, the second term, will correct or change from the standard state to the pressure of interest. You'll then add that to the molar Gibbs free energy under standard conditions and get the new Gibbs molar free energy. If you were to plot that for an ideal gas, this plot is what you would see. At this point right here, we can consider that to be the standard pressure, and if we follow over horizontally, we get to the standard molar Gibbs free energy. And anywhere along this curve is going to tell us how an ideal gas's molar Gibbs free energy is going to change with pressure. Now, further information section 2 takes us beyond that into the idea of fugacity. In other words, we want to see how a real gas might respond instead of an ideal gas. And if I were to draw in modifications to this curve, what we would notice is that this line would start deviating below this, and then it would come up and pass this. So in this region, we're going to see that the molar Gibbs free energy is actually lower than what we would expect for an ideal gas. And in this region, it's higher than what we would expect. And so it turns out in this region it's a case where repulsive forces are starting to dominate, and in the lower region it's where attractive forces are dominating. And we're going to try to describe this deviation with the term fugacity, and that's going to be defined as F, and it's going to equal a prefactor times pressure of the ideal gas. So fugacity is going to equal the fugacity coefficient times the pressure of the ideal gas. And that'll allow us to put into the mathematics treatment for non-ideality. And so right at this point is where we see that variation from attractive to repulsion. You'll hopefully see some analogy or analogous concepts to the treatment of compressibility in gases from Chapter 1. So if we were to now look at a little bit better rendition of this plot, what you can see is that at low temperature in this region, the attractions are going to dominate, but as you get closer and closer to low pressure, it should again merge with an ideal gas. Once you go above this region, repulsion is going to dominate. So how should we go about thinking about this question, and how can we calculate perhaps what is this gamma term? So what we can do is take the idea of fugacity and put it into our equation for Gibbs free energy, and we can compare that with ideal. So I'm going to write those equations down, and let's see if we can make some sense of that. So molar Gibbs free energy minus molar Gibbs free energy at some condition prime for a real gas would be equal to, say, the pressure prime, pressure, and Vm dP, just like you would do for the derivation we saw in section 3.9. It turns out this is equal to, for a real gas, RT natural log, and since it's a real gas, we're going to use the term fugacity. And so fugacity at pressure P and fugacity prime at P prime. So we're going to say this is real. And then we could also write, and I'm going to use a superscript circle to represent an ideal system. We can think about the same idea here for an ideal system, ideal gas that being. We can see what is the difference in Gibbs free energy for molar per mole under the same kind of conditions, going from pressure P prime to pressure P. We're now going to have the molar volume of the ideal gas, and so we'll put the circle here to indicate its ideal. We can tell that that's equal to R natural log of the pressure divided by the pressure prime. So this is going to be for an ideal gas. Now, excuse me, we can subtract these two, and the difference between these two should be related to the fugacity coefficient, or the difference between those two. And what I'm going to do is take this subtraction and look at the integral term and then the log term. And what we'll see, notice that the integration limits are the same. And so since we're going to subtract the bottom one, we're going to end up with the integral from P prime to P of the molar volume of the real gas minus the molar volume of the ideal gas, dP. And this is going to equal, notice we can factor out the RT terms, and so we'll have RT, and then it's going to be parenthesis natural log of F over F prime minus natural log of P over P prime, which we can rewrite as RT natural log F P prime over F prime P. Now what we want to do is think about applying some limits, and what we're going to do is say in the limit that P prime goes to 0. If that's the case, then P prime should equal F prime. In other words, the real gas starts to behave like an ideal gas. And if that's the case, notice over here, you'll see the P prime and the F prime can cancel. And we're going to then set this integral to 0. So I will rewrite that here, integral from 0 to pressure. And again, this will stay the same. The molar volume of the real gas minus the molar volume of the ideal gas is going to equal natural log of fugacity divided by pressure. And notice I'm missing an RT term. I'm going to put that over on the left-hand side just for convenience. And we have defined fugacity as equaling gamma times pressure. So if we put that in there, we're going to see that we're going to have the natural log of gamma times pressure over pressure. Pressure will cancel, and we end up with the natural log of gamma. So now we have an expression for the natural log of the fugacity coefficient. So if I were to write this in a bit of a condensed form, we'd have the natural log of gamma equaling 1 over RT integral from 0 to pressure of interest, and that should be molar volume of the real minus molar volume of the ideal dP. So conceptually, maybe what you can see is that we're adding up all of the differences in molar volume between the real gas and the ideal gas from 0 to the pressure of interest, dividing it by RT. That will then equal the log of the fugacity coefficient. Well, we know something about the ideal gas molar volume. We know that PVM equals RT. So we also know that Z for real gas is defined as pressure times molar volume over RT. And so we have a way we can maybe relate back to Chapter 1, ideas of compressibility. So from the upper equation, we're going to see that Vm ideal is equal to RT over pressure. And from this equation, we're going to see that Vm equals Z RT over pressure. So if we take the ideal gas component and the real gas component, plug them into this equation, essentially what we're going to see is the term Vm minus Vm naught is going to be ZPT, try that again, Z RT over P minus RT over P. So we can factor out the RT and rewrite this term as RT Z minus 1 over pressure. So let's take this and plug it in to the inside of the integral and see what we get. So now we're going to have the natural log of the fugacity coefficient equaling RT over RT, because the RT term will go through the integral. You're going to have 0 to pressure, and then what's left inside the integral is Z minus 1 over pressure dP. So these cancel, this goes to 1. It's supposed to look like a 1. And I will rewrite the final equation. So we have the integral of the compressibility minus 1 divided by pressure times pressure integrated from 0 to P. So here we have a nice way to define what the log of the fugacity coefficient actually is. If you remember an example for compressibility being Z equals 1 plus B prime times pressure plus C prime pressure squared, and so on, we can move the 1 to the other side, and you'll have Z minus 1. We can also divide by pressure, and we notice one pressure term will cancel, and z minus 1 divided by p, if you use the virial expansion in pressure, is going to equal b prime plus c prime times p, and so on, depending on how far you would take that. So we essentially have the answer, and if we're interested in trying to visualize what the log of the Fugacity term looks like, we can add a little figure here. So this is a figure from Atkins, and what we see is that the Fugacity coefficient Fugacity coefficient plotted versus reduced pressure for very high pressures, so 100 times the critical pressure, and the terms here are reduced temperatures. You can see that in this case we're quite above 1. 1 would be a Fugacity coefficient in which an ideal gas would equal a real gas. As you get closer to reasonable pressures or low pressures and temperatures much closer to condensation, you can see very similar behavior of the Fugacity coefficient with that of the compressibility from Chapter 1. Okay, well that concludes the derivation that's presented in further information section 3.2 in Atkins. That is the 9th edition, page 129.